talk about what a limit is today and two methods of evaluating. Okay, you don't know what a limit is, that is fine. Okay? But why is this picture funny? And what can't that touch? Okay, that curve is not going to cross our vertical axis. Okay? There you go. Okay. Definition of a limit. Please read through it. We will talk about it, but I want you to read through it first. Okay. L is the value of our limit. C is the x value that we are approaching. Okay? So as our function becomes arbitrarily close, what does arbitrarily close mean? Okay. We're almost there. We're basically there, but we're not there. Okay? We're coming very, very close. Okay? So, as we get close to this number from either side of C, our limit is C. Okay, so first of all, here's our notation. The limit as x approaches C of f of x equals some value L. A majority of the time, we will have a value for our limit. Okay. C, that is the x value that we are approaching from either side. Okay, we're going to look at it from both sides. Okay, and the limit is the function value we're approaching. Okay, so I want you to look at this picture right here. This picture is the limit as x approaches 2 of f of x. Okay, and so here's our f of x curve. Okay, so what we look at, if we follow our function along its curve, okay, since we're approaching 2, we're going to follow our function from the right of 2. We're going to follow the function from the left of 2. And the closer and closer and closer we get to 2, what is our function value? We're getting close to 4. So our limit is 4. What function value are we getting arbitrarily close to when we follow our function from both sides of that C value? Okay, that is what a limit is. Okay. Me? Okay. Questions? Okay. Okay, so I want you visually, when we look at these graphically, okay, just visualize riding a little train along the curve from either side. Where's that train? Sure, where's that train going to wreck into each other? Okay. Okay. Since we're looking at 2, we're getting close to 2, and our height is 4.
Is there always going to be like that point, or what is
we're basically looking at the height. Now, do we have a value at x equals 2? No, it's a hole. We don't have a value there. But we can evaluate the limit. Okay, that's what's special about a limit. There may not be that point there, but we can figure out what the limit is. Okay? Now, we can evaluate the limit almost anywhere on a function. Okay? you kind of brought up a good point with that pole being there, and we'll look at that a little bit more in a little bit. Okay. So basically, what we need to have in our minds right now is that when we come from the right and left side, we're approaching a value, right? Okay. So let's look at this in a chart. Okay. Here I have this limit right here. Okay, and C can be any number. All right. We have the limit as x approaches -1 of x squared minus x minus 2 over x. Okay. Now I have this chart. Okay. Why did I pick these numbers? Okay, first of all, we're looking at the limit as x approaches -1. So here I have my -1, right? These numbers over here, -1.1, -1.01, -1.001.
Close to the whole
Okay, they're getting closer from the,
L.
from which side? Okay, so these values are getting closer to our C value from the left. These values are getting closer to our C value from the right. So pod 1, I want you to plug -1.1, -1.1 in. Pod 2, -1.01. Pod 3, -1.001. Pod 4, -0.999. Pod 5, -0.99. Pod 6, -0.9. This is another way of looking at the limit. Okay, this is not going to be a strategy that we're going to use very often. Okay, this is just, we're getting the concept right now. What's happening? You can use your calculator.
Oh, okay.
Pod 1, do you have a value for me? Yes, what is that value? Your numerator needs fractions, your denominator needs, or parentheses. Negative 3 point something. You should get negative 3.1. Was that what you got? Okay. Caleb? Negative 3.01. Pod 3? Interesting. Okay. Pod 6. Negative 0.9. Adam?
No, that's
Negative 2.9. Okay. Pod 5?
Oh, I got that. We got 2.99.
Okay. So, as we come from the left of -1, and as we come from the right of -1, what function value are we approaching? 3. So that is our limit. Okay. Let's look at this graphically. What kind of function are we working with? We are. Right now it's a rational function, right? How do we graph rational functions? What's the first thing we have to do? Okay, we have to simplify, right? What is our numerator factor to? So what can happen? And we're left with x minus 2, but what is happening? What, Jay?
I thought when it cancels, it just makes a whole.
Yeah, it does. Okay, so we have f of x equals x minus 2, but what's special about it? There is a hole at x is negative 1 because we canceled that factor out. But it's still a line because that's what it reduced to. Okay? So this is the graph of our function. Right? Well, here is x is negative 1. As we approach negative 1 from the right, and as we approach negative 1 from the left, what function value are we getting arbitrarily close to? Negative 3. Okay? Which is what we decided our limit was. Okay. Now, using this picture, what if I asked you about the limit as x approaches 2? What would you tell me? As we follow our function from the right of 2 and from the left of 2, as we get arbitrarily close, our function value gets arbitrarily close to 0. Right, but the limit we're just getting close to. Okay? But yes, there is a point there at 2, 0, which will come into play in a little bit, so I want you to remember that. Okay? Now, there are 3 times a limit does not exist. You need to know these 3 times. Okay? Now, I've been emphasizing we're coming from both sides, right? Okay. If you evaluate a limit where the right and the left side are approaching 2 different values, the limit does not exist. Like this picture right here. Okay? We have a break in the graph at x equals 3. As we approach 3 from the right, we are at 4. We get close to 4. As we approach 3 from the left side, we're getting close to 1. Those are different, and so the limit doesn't exist. Okay? You have a break in the graph. All right? You cannot evaluate the limit at the break. Okay, I can evaluate the limit at 0, 1, 2, okay, but we cannot evaluate it at 3. Because we're approaching different values from the right and left. Second time, we don't have a limit. Is when we are increasing or decreasing without bounds. Okay, the examples that we're going to look at in this class is basically a vertical asymptote. Okay, if I ask you to evaluate a limit, what happens at a vertical asymptote? What is the graph doing? Okay, it's approaching it. It goes either up and up and up and up and up without touching it, or down. Okay? Yes. All right? If we're talking about the limit at that asymptote, okay, it is going to keep rising or keep falling. It's not approaching anything. So we describe it as the limit doesn't exist. Okay? This is a case where in calculus we go a lot more in depth with, and we can actually describe it in different ways. But in this class, we're just going to say it doesn't exist, and then next year in calculus we're going to explore that a little bit more. Okay. And then the third time is when we have a function that oscillates between 2 values as we are approaching C. Okay? As you notice in my picture, the limit as x approaches 0 would not exist, because as we come from the right and left, we are oscillating between -1 and 1 faster and faster and faster. We don't know what's happening in there because it just keeps bouncing back and forth so quickly. you need to remember these three cases. Any questions about that? Okay. Okay. These are the 3 times where a limit doesn't exist. You will be questioned on it. Mean Girls. Okay. They're in a calculus competition. Yes? No?
Oh,
Yeah.
okay.
Okay. You two have been quoting it the whole time. Okay. I know I'm not going to be able to use this for very much longer because the older I get, the less familiar you guys are with this one. Okay, now, Caleb and Caleb were both kind of talking about, well, isn't there just a coordinate there when we've been evaluating limits? Okay, have you noticed that? Okay, we have a method, and a numeric method to evaluating limits without having to look at its graph. Okay, so if we have a polynomial function, and we're evaluating a limit. Now, what's true about a polynomial function? What do they look like? Give me an example of a polynomial. A parabola. A cubit, a quartic. Okay? They all are nice, smooth curves that go on forever. Right? Okay. So, as long as we have a polynomial function, we can do what's called direct substitution. Okay? If you have a limit of a polynomial, you basically can plug that c value in and you get the limit. Why is that? You were saying it earlier. Because there's a point right there. Yeah, and that is the coordinate that we are approaching. And so let's just evaluate that coordinate. Because that is what we are approaching. So here we have the limit as x approaches -1 of x squared plus x minus 6. This is polynomial, so we can use direct substitution. Okay. What is that value? Let's look at the graph. Okay, here's the graph, x squared plus x minus 6. If I look at, we're at -1. Okay, there's my coordinates, -1, -6. Okay, as we approach our function from the right of -1, as we approach our function along our function from the left of -1. Okay, we're getting arbitrarily close to that coordinate, -1, -6. So our limit is -6. It's important that you guys can think of what is happening graphically as well as what's happening numerically. Okay, connecting those together is good. Okay. All right. We can also do direct substitution with rational functions as long as c does not make the denominator 0. If the limit that we are finding makes the denominator 0, we have to use a different approach, which we will talk about tomorrow. Okay? As long as our denominator is not 0, then we can evaluate the limit by direct substitution. have the limit as x approaches -1 of x squared plus x minus x over x plus 3. Does this c value make our denominator negative? I'm sorry, does this c value make our denominator 0? No. So we can use direct substitution without a problem. And what is our limit? -2? Okay. Three? I'm just, you guys are telling me. 3? -3 though? Okay. We're in disagreement. Isn't this 1 minus 1?
Yes.
So we have -6 over 2. Okay. Now let's think about this graph. Okay? When we graph a rational function, what do we have to do? Factor first. X plus 3 times x minus 2. And we have something that cancels. So we have a line with a hole again, don't we? Same line, different hole. Where's our hole at? Okay. So if you look at, here is the limit as x approaches -1. Okay, if we follow from the right and left, we're approaching that coordinate -1, -3. So our limit is -3. Now, if I ask you to evaluate the limit as x approaches -3, x squared. If I asked you to evaluate this limit, you would not be able to do it by direct substitution, would you? Because this value makes our denominator 0. Right now, our only solution is to look at the graph. Here I have the graph. What is the limit as we approach -3? -5. Okay? That's where that hole is, right? As we get arbitrarily close to -3, we're getting arbitrarily close to that -5. Where the hole is. There's either a hole or an asymptote. Okay, and that is something that we're going to talk about tomorrow. It is a technique that if our value makes the denominator 0, is there a way to still evaluate it? Okay, either two things are going to happen. It's going to be a hole and we're going to somehow be able to evaluate it, or it's going to be an asymptote, so it's not going to exist. Okay, so we'll talk about that tomorrow. All you have to worry about today is deciding whether a limit exists or not based on a graph, evaluating a limit on a graph, and evaluating a limit by direct substitution.